Dear students, this is the second part of our unit electromotive force, and in this recorded class we will be learning about the Nernst equation, derivation for Nernst equation for the electrode potential and cell potential, then Gibbs Helmholtzequation and EMF of the cell, calculation of free energy, enthalpy and entropy from the EMF data. You shall take section 3.7 EMF of the cell in your text, page number 172. So these portions we have seen in the previous classes. So what is meant by an EMF of a cell? EMF, it is a short form of electromotive force. So every galvanic or voltaic cell is made up of two half cells. The oxidation half cell, that is the anode, and the reduction half cell, which is the cathode. So one of the electrode must be having a higher potential. So it will be having a higher tendency to lose the electrons when compared to the other electrode. As a result of this, a potential difference is created. So the potential difference is a result of this difference in the electrode potential. So one electrode will be at a higher potential, that is, it will be having a higher tendency to lose the electron, whereas the other electrode will be of a lower potential. So the potential difference resulting from this causes a flow of electrons from an electrode at a higher potential to an electrode at a lower potential. So this is a case which is similar to all other cases, like if a higher pressure region and a lower pressure region is coming in contact, so gas will flow from a higher pressure region to a low pressure region. Similarly, if you are mixing two solutions of different concentration, the molecules or the ions will flow from a higher concentration region to a lower concentration region. Similarly, in the case of electrode potentials also, the electrons will flow from a higher potential region to a lower potential region. So the difference between the electrode potentials of the two half cells is known as electromotive force or EMF of the cell. It is also called cell potential. So you can expect questions like define EMF. So EMF is the difference between the electrode potentials of the two half cells. EMF is also called electromotive force or a cell potential. So how will you calculate the EMF of a cell? So the EMF or E cell of a galvanic cell is given by the expression E cell is equal to E of cathode minus E of anode. We have seen this formula earlier. So here E of cathode and E of anode are the respective reduction potentials of the electrodes acting as cathode and anode in the cell. But E of cathode, E of anode, this is reduction potentials. We have learned about reduction potential and oxidation potential. So when we are calculating the EMF of a cell, we are considering the reduction potentials of both the cathode and the anode here. Since in the conventional representation of the cell, cathode is written on the right and anode on the left, we may write the expression for EMF, that is E of a cell, as E cell is equal to ER minus EL. So this is the formula for calculating the EMF of a cell. So here ER is the electrode potential of the right-handed electrode and EL is the electrode potential of the left-handed electrode. So these two are the reduction potentials. So if a positive value of EMF or E of a cell is obtained, it means that the cell reaction is feasible. We have learned about how to determine the feasibility of a cell reaction. The cell reaction feasible ആണോ ഇല്ലയോ എന്ന് മനസ്സിലാക്കുന്നത് എങ്ങനെയാണെന്ന് നേരത്തെ പഠിച്ചിരുന്നു. അതായത് ഇ ഓഫ് എ സെൽ കാൽക്കുലേറ്റ് ചെയ്യുമ്പം അതൊരു പോസിറ്റീവ് വാല്യൂ ആണ് തരുന്നതെങ്കിൽ that means that the cell reaction is feasible. അപ്പോൾ അങ്ങനെ ഒരു ഫീസിബിൾ സെൽ റിയാക്ഷൻ്റെ ഡെൽറ്റ ജി വാല്യൂ നെഗറ്റീവ് ആയിരിക്കും അല്ലേ. ഓക്കെ, നെക്സ്റ്റ് we will learn about Nernst equation. This also we have seen previously, but we will learn how to derive Nernst equation. So we can expect this question: derive Nernst equation for the EMF of a cell. Please take the section 3.71, effect of electrolytic concentrations and temperature on the EMF of a cell. Nernst equation for EMF of a cell. So the electrode potential and the EMF of a cell depend upon the nature of the electrode, temperature and activities അല്ലെങ്കിൽ concentration of the ions in solutions. The variation of electrode and cell potential with concentration of ions in solution can be obtained as follows. Now we are considering a general reaction like this. A molecules of capital A. So this is a number of moles. Small a is the number of moles here. A is the species or the molecule. A plus B giving M plus N. So this is a general reaction, and we imagine that this type of a reaction is occurring in a cell. So according to Gibb's reaction isotherm, the free energy change is given by G is equal to G0 plus RT ln Q. And if this free energy change is considered, we replace this G using delta G. So the equation becomes delta G is equal to delta G0 plus RT ln. We take the product side of the equation first. That is concentration of M raised to M into concentration of N raised to N. So this is the numerator, and divided by, then we consider the reactant side, that is the concentration of A raised to A. You can see here into concentration of B raised to B. So this is a expression for delta G. Let us see how the equation is changing. So the decrease in free energy of a chemical reaction appears as electrical energy in an electrochemical cell. That is minus delta G is equal to NF E of a cell. So E of a cell is the EMF or the electromotive force. So at the standard condition, we change this equation as minus delta G0 is equal to NF E0 of the cell. Now putting these into the above equation. So we are putting the value of delta G and delta G0 into equation 14 here, and we get this equation number 15 as minus NF E of a cell is equal to minus NF E0 of the cell plus RT ln concentration of M raised to M into concentration of N raised to N divided by concentration of A raised to A and concentration of B raised to B. This is equation 15. Again, we can change this equation in terms of E cell. So we have to bring this minus NF term to the other side, that is below RT. So the equation changes to E of a cell is equal to E0 of a cell minus RT divided by NF ln concentration of M raised to M into concentration of n raised to n divided by concentration of A raised to A into concentration of B raised to B. Or we can write it in terms of log. So we have to introduce the term 2.303 in the equation. So the equation becomes E of a cell is equal to E0 of a cell minus 2.303 RT by NF log m raised to m into n raised to n divided by A raised to A into B raised to B. So this equation is known as the Nernst equation. So this is a derivation for Nernst equation. You have to learn this. Suppose if the E of a cell has to be determined under the standard condition at 25 degrees Celsius, then we can substitute the value of temperature and R, that is a Rydberg's gas constant, in this equation. Subsequently, the equation will become as follows: E of a cell is equal to E0 of a cell minus 0.0591 by n log m raised to m into n raised to n divided by A raised to A into B raised to B. So if for examination problems are asked and the temperature is specified as 25 degrees Celsius, then you can use this formula directly. Suppose if the temperature is not 25, some other values are given, you have to take the Nernst equation, the equation 17, directly for the problems. Let us see the thermodynamics of cell reaction now. Okay, so you know the Gibbs-Helmholtz equation. Gibbs-Helmholtz equation is given in equation 19, that is delta G is equal to delta H plus T dou by dou T of delta G at constant pressure. You can see P written as a subscript of the bracket. So it means that the change of delta G with respect to temperature at constant pressure condition is determined. Okay, so in this equation we are substituting the value of delta G. Delta G, we know that it is minus n of E of a cell. So we take the expression for T into dou by dou T of delta G at constant pressure is equal to minus n of T into dou by dou T of E of a cell at constant pressure. So we are putting the value of delta G directly here. So here we know that N and F are constants. Therefore we take the term outside the square bracket, that is minus NF will come outside the bracket, and we get this equation 20 here. Now this equation 20 can be written as E of a cell is equal to minus delta H by NF plus T into dou by dou T of E of a cell at constant pressure. So here this part, that is dou by dou T E of a cell at constant pressure, this is known as the temperature coefficient of EMF of a cell. So this is the temperature coefficient. Define temperature coefficient of EMF of a cell. You have to write this expression dou by dou T of E of a cell at constant pressure. That is the change in EMF of a cell with respect to temperature at constant pressure. So this equation 21 shows that whether the electrical energy NFE produced is greater than or less than or equal to the decrease in enthalpy, that is minus delta H. So here if this term, this temperature coefficient, if it is greater than this minus delta H, or if it is less than delta H, or if it is equal to delta H, three conditions can be understood here. So this is summarized in the following section. Let us see the first. If dou by dou T at constant pressure is positive, so if this value is positive, then what is the inference? It is that if the EMF of the cell increases with rise in the temperature. If the EMF of a cell is increasing with the rise in temperature, that is, this value will be positive. So the electrical energy will be numerically greater than the enthalpy of the reaction. Okay, so this minus delta G, you have to consider this value, and the electrical energy will be greater than this enthalpy of the reaction. That is numerically. We should not consider the sign here, only the numerical value of the enthalpy. Now let us see the second condition. If this temperature coefficient, that is dou E by dou T at constant pressure, is negative, it means that if the EMF of a cell decreases with rise in temperature, that is, the electrical energy will be numerically less than the enthalpy of the reaction. That you can understand from this expression. Here, this term is less than the enthalpy of the reaction. Okay. Again, there is a third condition, that is dou E by dou T at constant pressure is equal to 0. So this means that the electrical energy will be numerically equal to the enthalpy of the reaction. So this is a relationship between the Gibbs-Helmholtz-Equation and the EMF of the cell. Now we can see the thermodynamic factors, that is a relationship between heat change delta H and electrical energy E. So first we take the Gibbs-Helmholtz equation here. Gibbs-Helmholtz equation is delta G is equal to delta H plus T dou by dou T of G at constant pressure, where this delta H is the change in enthalpy, and we know that delta G is minus NF E. So this delta G is connecting the electrical energy of the cell, or the EMF of the cell. So we are substituting this minus NF E in this equation. Minus NF E is equal to delta H plus T into dou by dou T of minus NF E at constant pressure. Okay, here this G is also substituted with minus NF E. So since minus NF is a constant, we are taking this outside. So the equation now becomes NF E is equal to delta H minus NF T dou by dou T of E at constant pressure. And this can again change as delta H is equal to minus NF E plus NF T dou by dou T of E at constant pressure. Here this term, we know that it is the temperature coefficient of EMF. We have seen that previously, dou by dou T of E at constant pressure. So the conclusions from this equation 23 is given below. So you see that this equation is connecting delta H, that is the enthalpy change, and the electrical energy of the cell. So let us see the first conclusion. If dou by dou T of E at constant pressure is 0, if this part is 0, then delta H will be equal to minus NF E. And the second condition, if dou by dou T at constant pressure is positive. So if this part is positive, then this NF E will be greater than the enthalpy change of the cell. Again, the third condition is that if this temperature coefficient is negative, Then we know that we have there are two negative values here. This part will be negative and this part will also be negative. So NFE will be very less than the enthalpy change. So these are the three conclusions from the equation connecting delta H and electrical energy. Now let us see the relationship between entropy change delta S and electrical energy of the cell. So we know this thermodynamic equation, G is equal to H minus Ts. Here G is the Gibbs free energy, H is the enthalpy and S is the entropy, and you know T is the temperature. So for a given change at constant temperature, here the temperature is kept constant, and we imagine that the some reaction is occurring and the free energy and enthalpy and entropy are changing. So the equation will become delta G is equal to delta H minus T delta S. Now delta G minus delta H is equal to minus T delta S. This is from the thermodynamics only. Then according to Gibbs-Helmholtz equation, we know that delta G is equal to delta H plus T dou by dou T of delta G at constant pressure, or we can write it like this: delta G minus delta H is equal to T into dou by dou T of delta G at constant pressure. We are bringing this delta H term to the left hand side. So we know that this thermodynamic equation and the Gibbs-Helmholtz equation, the left hand side becomes the same. Therefore, we are equating these two right hand sides. That is minus T delta S is equal to this part, T into dou by dou T of delta G at constant pressure. From this equation, we can get the expression for delta S as minus dou by dou T delta G at constant pressure. So here our motive is to connect or derive a relationship between delta S and the electrical energy or EMF of a cell. But we know that delta G is equating to EMF as delta G is equal to minus NF E. So we combine these two equations and we get this relation: delta S is equal to minus dou by dou T of minus NF E of a cell at constant pressure. So here these two minus will get cancelled, it will become positive. So the delta S value will be delta S is equal to NF dou by dou T of E at constant pressure. N and F are constant, so we are taking this outside of the derivative term, and this is the expression, resulting expression connecting delta S and E. Now let us see a few solved problems in your text. Problem number 3. Calculate the reduction potentials for the following half cell at 298 Kelvin. So in this question it is given as 298 Kelvin. So you can directly take this Nernst equation form: E is equal to E0 minus 0.0591 by N log this expression. So here one thing you have to notice that the half cell is given. ഈ പ്രോബ്ലത്തിൽ half cell reaction ആണ് തന്നിരിക്കുന്നത്. So only one of the part of the reaction is represented in this. So here it is the reduction reaction given, that is Ag plus an electron giving Ag. This is the reduction reaction only. Only half part of the cell reaction is represented here, and you are asked to calculate the reduction potential for the following half cell. So you know the temperature here, and you also know the concentration of Ag plus, that is 0.1 molar, and the standard EMF, standard E of the cell, of the half cell, is given as 0.8 volt. So this reduction potential is actually the potential for converting, for reducing Ag plus to Ag. Okay, the first term is Ag plus here. So this Ag plus is being converted to Ag, and the potential for this reaction is 0.8 volt. So we are substituting all the values we already know from the question in this Nernst equation. So E0 is 0.8, which is given here, and the concentration of Ag plus is 0.1 mole, and the resulting answer is 0.741 volt. Let us see the next question. Calculate the EMF of a cell at 298 Kelvin. So here you have to note that the complete cell is represented here, and the oxidation and the reduction reactions are given here. So you have the anode and the cathode, both are given in the question, and in this question you can see a nickel rod dipped in Ni2 plus ion solution, which is again the other half cell is Ag rod, silver rod dipped in silver ion solution, and a salt bridge is separating these two half cells. This is a complete electrochemical cell, and the E0 of this reaction for reducing Ni2 plus to Ni is given as 0.25 volt, and E0, that is the reduction potential for converting Ag plus to Ag, is also given as 0.8 volt. So these two are the standard reduction potentials which can be directly obtained from the electrochemical series only. So from these data you are asked to calculate the EMF of the following cell. So for finding the EMF, you can directly take Nernst equation shown here, because it is given as 298 Kelvin. So the temperature will be 298 only. So in this Nernst equation, first you have to calculate the E0 of the cell. Here in the question, E0 of the two electrodes are given only, and from these two you have to first calculate the E0 of the cell using the formula. E0 of the cell is equal to E0 of cathode minus E0 of anode. So here the E0, the cathode will be the one at the right side, anode will be the one at the left side. So here the cathode is silver. So silver, the reduction potential is 0.8. So you have to substitute the value of 0.8, then minus 0.25. Here there is a small twist here, because in the question it is given the reduction potential for converting Ni2 plus to Ni. But when these two cells are connected, so this nickel is first being oxidized here. Okay, so the reaction is a reverse here. So it is 0.25 negative of 0.25. Okay, so this you have to be careful while attempting questions like this. So the anode, it is the oxidation happening, but in the question you will be given the reduction potential only. So you have to take the negative value of the reduction potential here. So the answer is 0.8 minus of 0.25 is equal to 1.05 volt. Then substituting the value of E0 of the cell in the Nernst equation, you will get the final answer as 1.0795 volt. Let us see the problem number 5. Calculate the standard Gibbs free energy delta G0 for the reaction occurring in Daniell cell. So the Daniel cell reaction is given as zinc plus copper 2 plus giving zinc 2 plus copper. So this reaction is at 298 Kelvin and the E0 of the cell at this temperature is 1.1 volt. Find this reaction is spontaneous or not, that you have seen earlier. So first we have to see the value for delta G0. Okay, delta G0 is equal to minus N of E0. So here N is the number of electrons involved in this redox reaction, that is 2, and F is the Faraday 96,500, and E0 of the cell is also given as 1.1 volt, and we get the answer of delta G0 as minus, here it's a negative here, minus 212.3 kilojoules. So here we see that this delta G term is negative. So it means that the cell reaction is spontaneous. Let us see the problem number 6. So the following chemical reaction occurring in an electrochemical cell is magnesium plus 2 silver plus ion giving magnesium 2 plus and 2 silver. So calculate the cell potential of the system. Given the standard EMF of reduction for magnesium, reduction of magnesium 2 plus to magnesium is minus 2.36 volt, and standard reduction potential for silver for converting Ag plus to Ag is 0.81 volt. So in this portion, E0 of the cell is E0 of cathode minus E0 of anode. So here there is a positive sign here because the negative of negative will become positive. So this is the anode part. So the equation will give this answer, that is E0 of cell is 3.17 volt. And we are substituting this E0 of the cell in the Nernst equation. Here it is E of a cell. E of a cell is equal to E0 of the cell minus 0.59 by 2 log concentration of magnesium ions divided by concentration of silver ions square. So here in the equation you can see that for 1 magnesium you need 2 silver ions. So that is why here Ag plus square is appearing, the square term is appearing. And for the pure state, pure solid state, the concentration of silver as well as magnesium will be 1. So that we are not representing in the formula. So you obtain the final answer of E of a cell as 2.96 volt. So here also you see that the cell EMF is positive. Okay, it is positive, therefore the reaction is feasible. Then the problem number 7, that is a zinc rod is dipped in 0.1 molar solution of zinc sulfate. So the salt is 95% dissociated at this dilution at 298 Kelvin. So to calculate the electrode potential given that E0 of zinc 2 plus to zinc conversion, the reduction potential is 0.76 volt. Here also there is a small correction from your text. This is a negative 0.76 volt. From electrochemical series you can see that the original value is negative only. Okay, so in this case also first you have to take the Nernst equation and substitute the value of concentration of zinc ions. For the concentration of zinc ions, you have to multiply it by the percentage of dissociation. So if it is 0.1 molar, you have to multiply it by the 95 by 100. Then you get the concentration of active zinc ions present in the cell. So this is the concentration of zinc ions, 96 by 100 into 0.1 molar, and this is the molarity of the zinc ions. You have to substitute the value in the Nernst equation and you get the E of the cell as minus 0.79021 volt. Again, in problem 8, calculate the equilibrium constant K for the reaction at 298 Kelvin. So this is a reaction. Cerium 4 plus is being reduced to cerium 3 plus, while Fe2 plus is being oxidized to Fe3 plus. So given that the Fe3 plus to Fe2 plus reduction potential is 0.771 volt. But in the actual reaction, this Fe2 plus is being converted to Fe3 plus. So you should remember that for substituting in the question, you have to take the negative of this value. Okay. And you also see that in the question, E0 of the reduction potential of Ce4 plus is given. Ce4 plus to Ce3 plus conversion, the reduction potential is 1.61 volt. So you can substitute all these given values in the Nernst equation. First, you have to write the cell reaction. So the cell reaction, the electrodes are platinum in both the solutions. So platinum, Fe2 plus, Fe3 plus, salt bridge, Ce4 plus, Ce3 plus, platinum. So this is a cell reaction. So for the cell reaction, the EMF, the standard EMF is obtained by subtracting the E0 of the right hand side and E0 of the left hand side. So here E0 of Ce4 plus Ce3 plus minus E0 of Fe3 plus Fe2 plus. So you get the value of E0 as 0.839 volt. Now you have to connect it with delta G. So delta G0 is equal to minus NF E0 of a cell. So from this E0 of the cell, you can calculate the value of delta G0. And you know that this delta G0 is connected to the K, which is the equilibrium constant of the cell reaction. So now you can find the value of K from the delta G0 value. You have to take the antilog of this value and obtain the final answer. And this is the 9th problem. Calculate the EMF of a cell. Here this is a cell having a copper and a silver part connected using a salt bridge, and this is the cell is at 298 Kelvin. We are given the E0 of that is the reduction potential of Cu2 plus to Cu as 3.34 volt, and E0 of Ag plus to Aj is 0.8 volt. Here also there is a correction. If you see the electrochemical series, you can know that the value is 0.34 volt only. So it is not 3.3, it is 0.34 volt. So in this also, for calculating the EMF, you take the Nernst equation, and you can see that in this E0 of cell has to be calculated first. For that, you have to subtract these two values, that is the E0 of the right hand side electrode minus E0 of the left hand electrode. So first you have to get the value for E0, which is 0.46 volt, and here N is 2, and the value, the concentration of Cu2 plus ions is 0.25 molar, concentration of Ag plus ion is 0.6 molar. So substituting these two values in the equation, you get the final E of a cell, the value for E of a cell as 0.464681 volt. Again, the last problem, calculate the EMF of a cell. Zinc 2 plus 0.001 molar salt bridge, Ag plus 0.01 molar Ag. Here also given the reduction potential for converting Ag2 plus to Ag is 0.8 volt, and the reduction potential for zinc 2 plus to zinc is minus 0.76 volt. So you have to calculate the EMF of the cell from all these values. So here take the Nernst equation and can give all the values here in the equation. E of a cell is equal to 0.8 volt. You will get that E of a cell 0.8 volt minus of 0.76 volt. Okay, these two values you have to subtract and get the E0 of the cell. Then E of a cell will be the final answer 1.58955 volt. So you have to do this problem, and the problems are a sure question, so do not miss this problem section.